Welcome, Space Cadets. We're about to start our topic, the universe. We're going to start with the driving force for the entire universe, the very, very weak force that is gravity. This image here was taken by astronaut Neil Armstrong on their last day on the moon. Alright, what's the point? By the end of this, you need to be able to define gravity. You also want to be able to explain a little bit about it. For example, what young Galileo Galilei is doing right here. Okay, so what is gravity? Now, this is some maths here. You need to be able to kind of recognize it. You don't need to be able to do it. Now, extremely weak attractive force is what gravity is, and it's between any two objects in the universe. And that's the cool thing. There is gravity between you and any star or object at any point in the universe. It is the driving force or the driving engine of most objects in the universe, and it's why everything is large is also round. So the size of the force essentially depends on the mass of the objects and the distance apart, and that's what we see here. But it's always there, so it doesn't matter how far apart something is away from you, you are always a little bit attracted to it. It's an attractive force. Now, generally, when things are moving through space, it is a small force. It is a weak force, but a small force over a long time can add up to an amazing velocity. We also have the gravitational constant, which is this number here. So the way this works, it is the mass of object 1 times by the mass of object 2 divided by r squared, which is the distance between them, and it's from the very center. So the distance between them, r squared. So mass 1 times mass 2 divided by r squared. And this is all multiplied by the gravitational constant. Now, if we have a look, you'll notice that it is times 10 to the minus 11, which means it is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 6, 6, 7, ... So that's it. It's a very, very small number. It's a very small number. So the gravity between two people who are sitting right next to each other is 1 micronewton, which is a millionth of a newton. All right. So gravity on Earth. Basically, on Earth, all objects fall at the same rate, and this excludes interference from air. So if you dropped a hammer and a feather, they're going to fall at different rates. And we see this here, okay? So this is why. If you've got a large object, because gravity is mass times mass, it will be 100 newtons times that. If it is a small object, it is 10 newtons times that. So it's, yeah, so you get the point. So on the moon, you don't need to that much. Just know that everything falls at the same time, same rate. On the moon, gravity is 1/6 that on Earth because the moon is 1/6 the size of the Earth. So that would be this times 6. Then you divide it by 6. So it means this times 1. And you get a smaller number. So the Earth is 1/6 the size of Earth. So the moon is 1/6 the size of Earth. So gravity is 1/6 of that. Now weight is a function of gravity. So weight is not your mass. Weight is the force. So it's the downward force. So the pull from you to the center of the Earth due to the mass of the two objects. For example, here we have the mass of 120 kilograms and the weight is 1200 newtons. Here the mass is 120 kilograms and the weight is 200 newtons. Here we see an astronaut on the moon. I believe that is Buzz Aldrin, because Michael Collins didn't come down, and Neil Armstrong has a big red stripe down his hat to show he's the boss. And here we have an astronaut going on a spacewalk. This is microgravity. It is not zero gravity. That astronaut is actually in free fall towards Earth, but so is the space station that he's attached to. Here is Neil Armstrong, the very first person to walk on the moon. There's the lunar lander. and there's the buggy, and that just would have been the best day ever. Yes, so that's why. So that's I don't know. That's the mood. That's rad. Be cool. All right. See you.